Today we're going to take a look at 7.4, and there's two things that we're going to do in 7.4. We're going to be looking at arc length, so the length of a curve, and then we're also going to be looking at surfaces of revolution as opposed to solids of revolution. And the surfaces of revolution is going to feel a little bit like our solids of revolution, and arc length is going to feel a little bit easier, I think, as a general statement. Adrian.
I just had a quick question about the homework for 7.4.
Okay.
It says due on missing homework on accident.
Yeah, I will get the dates fixed inside of WebAssign so that they're correct, but thank you for letting me know. All right, so 7.4, the first thing we're going to look at is arc length. So arc length is the length of a curve, and the length of anything, and you might sort of started maybe be thinking of like distance. If you were finding the length of a straight line segment, you would be finding distance, and you'd have a distance formula to be able to do it. So to find the length of a curve, we have an integral because we don't have straight objects. So for those of you who have used this textbook since the beginning, the very first thing that we did in this textbook together, like late in the fall, was that we talked about comparisons of pre-calculus to calculus, and this was one of them. Pre-calculus, we can find the distance of a straight line segment, but with calculus, we can actually find the length of a curve because there's curvature to it, right? And so the curvature makes it a calculus topic. If it were a very defined curve, like a circle, we could use some geometry. But we want to do this in general. So our curve, y equal f of x, if that's our curve, then the arc length is the integral from a to b of the square root of 1 plus f prime of x squared dx. And if we had it defined in terms of y, right, x is equal to g of y, we would have a very similar statement, much like when we were doing our our solids of revolution, and it would be the integral from c to d of the square root of y plus g prime of y squared dy. And I hope you can kind of see some of the distance formula embedded there, right? Distance formula has a square root in it, so do our arc length formulas. The distance formula has two pieces squared and added together. We've got, obviously, the derivative piece where you can see it squared, and 1 squared is itself. So there's a squared component there, and there's addition. So there's an embedded distance formula in here as well. So setup-wise, this is a lot easier than what we've been doing in 7.2 and 7.3. Computationally, might not necessarily be, because the derivatives and then the square root and the antiderivatives might become kind of complicated. So you give a little and you get a little. That's the way it is with a lot of things in life, right? There's one part that's easier, there's one part that's harder, and that's what we're going to have present here. Okay, is everybody ready to take a look at an example? All right, so our example is the curve y equals x to the 5th over 10 plus 1 over 6x cubed, and this is defined from 2 to 5, okay? So within our distance formula, or between our two distance formulas, what we're going to be looking at, our arc length formulas, is that this is the integral from a to b of the square root of 1 plus f prime of x squared and then dx. How do I know? Well, I know because it's actually given as y equals. That's how I know to use that one. If the equation were given as x equals, I'd be using the other equation. Easy enough? Okay.
Is there a difference between the equations aside from the function?
Nope, there's not at all. The limits need to make sure the limits are on the right variables, right? These limits are given to us on x. If we were doing something over here with y, we need to make sure we're using the limits on y. But that's the only difference, is to be careful of the limits of integration and that you're actually taking the derivative of the right thing. Yeah, but the formulas themselves are just the same, switched, okay? All right, so what do I need to do first? I need to take a derivative, right? The formula itself has a derivative in it. And so this is one of those places in the course. We experienced this when we do U substitution, where we're both doing derivatives and antiderivatives within the same problem, okay? So we do need to take a derivative of this. So this is f of x, and we need the derivative. So I need f prime of x. So if I do the derivative, the first one's sort of in a very nice form already. What's the derivative of x to the 5th over 10?
5x to the 4th over 2.
Right, 5x to the 4th over 10, which will simplify to x to the 4th over 2. I think you're kind of merging those together, Piers. Does that look okay for the first piece? Okay. The second piece you might want to rewrite, yeah? Do not move the 6th, but you can move the x cubed up as x to the negative third, right? So we need the derivative of 1/6 x to the negative third. So what would we get for that?
Negative 1/2 the x on the bottom squared.
Okay, so the 1/6 is going to stay, right? I changed the sign to be negative, and then I'm going to get a 1/2. So you're going to get x to the negative 2 and divide by negative 1/2. So I've got the 2 here. I changed the negative in front of the 6. Does everybody see where all my pieces went? Kind of separated things out a little bit. So this is x to the negative 2 over negative 2. The 2's here and the negative's here in front. The 1/6 stayed. Should I write it differently? Maybe I should. You guys are looking at me like I've lost my marbles. How about like this? There's a 1/6. I have x to the negative 2 over negative 2. Is that better? Everybody see where all the pieces came from?
I thought you subtract on, yeah.
Where'd you get the negative?
Oh!
half?
Because we mixed up our integrals and our derivatives, right? Yeah, Levi and I both did it together. I just listened to him. You're right. Let's try again.
Time change.
Fair enough. We'll go with time change as an excuse. That sounds like a good one. All right, let's try again. So the negative 3 should come down. Agreed? Negative 3, and then it would be x to the negative 4th. Thank you so much. I even warned us that we were doing derivatives and antiderivatives in the same problem, and we still just went right on past it. Wonderful. Okay. Need to clean it up, though. Agreed? So the negative still will come to the front. The 3 and the 6 will simplify, so we have x to the negative 4th over negative, over 2. Okay, is that all right? Because I'm about to take an antiderivative of this in a minute anyway, there's really not any necessary reason to put the x to the 4th back in the denominator. You're just going to bring it back up to the numerator in order to do an antiderivative anyway. So it probably is helpful to notice that they both have a 1/2 in the denominator, or they have a 2 in the denominator. So they have a power or a coefficient of 1/2. And so it's actually going to be a little bit nicer if I pull that to the front and I represent it like this. Okay, is that all right? Okay, so here is a form of our derivative, and we're going to put this into the formula in the right location. So thinking about this formula now, our antiderivative goes from 2 to 5. We were given that information. I have the square root of 1 plus, and then I have 1/2, and then x to the 4th minus x to the negative 4th, and all of that, including the 1/2, is squared. Okay, so far so good? All right, so the next thing I would do would be to square the components, right? So we'll square the 1/2. That's a 1/4. And what happens when I square x to the 4th minus x to the negative 4th?
Foil it.
You have to FOIL it, right? You cannot just square the components,
No, not right away.
okay? My Calc 1 students are still working through that too. Trig students, everybody wants to do it because it seems like it would be like, we'll just distribute it, right? We have this distribution property and we forget where distribution actually applies. It doesn't apply to addition in the middle or subtraction. So we actually have to multiply this by itself. So I'm going to write this out a little bit carefully within the problem. If you don't need to see it because you can just work through it, that's great. Go for it. But because it's an easy step to forget, I'm going to write it out carefully. So we have this starting there. Okay. So as we distribute this out, there's going to be some interesting things that are about to collapse. So we still have our 1 at the beginning. I still have my 1/4 here. I'm not going to mess with the 1/4 for the moment. X to the 4th times x to the 4th would be x to the 8th. What happens when I do the inner terms here? What is negative x to the 4th times x to the 4th?
X to the 0, which is 1.
X to the 0, which is 1, and it's negative because there's a negative sign here. So this is negative 1. Agreed? Okay. Now, that's not the only place that I have a negative 1. I also have it when I do the outside piece, right? So this one's also negative 1. And so I actually have what feels a little bit awkward because I have a constant showing up as the middle term. We'll talk about that later, but that's what it is. And then we have our last piece. X to the negative 4th times x to the negative 4th is... yeah, x to the negative 8, and it is positive since I have that negative times a negative. Okay, I'm going to distribute this fourth through. And at the same time, I'm going to rewrite the one at the beginning as 4 over 4 so that I'll be able to combine it in a moment. Okay? So I'm going to do kind of two small steps at once just to save a little bit of space. So this is 4 over 4. And then I have plus x to the 8th minus 2 plus x to the negative 8 over 4 dx. Okay, we good? Same denominator, so we can combine the numerators, right? So now have 4 and negative 2 that can be combined within that numerator, agreed? That's going to give me a 2. And I'd kind of like to leave it written in the middle. So I'm going to write this as x to the 8th plus 2 plus x to the negative 8 over 4 dx. Now, x to the 8th plus 2 plus x to the negative 8 looks an awful lot like this piece, doesn't it? Are you with me? If the piece in yellow came from x to the 4th minus x to the negative 4th squared, I'm going to have a very similar factoring that's going to go in reverse now for the one that I am working on here too. Let's talk about the 4 as the denominator as well. The 4 as the denominator is underneath the radical, agreed? So I can pull the 4 from underneath the radical out in front as a 2, correct? So in some sense, I can, well, not in some sense, it's actually a property. I can separate, I can't do this with the addition and subtraction, but with the 2 division pieces, I can. Let's do that. This is the square root on the top and the square root on the bottom. So there's a square root of a 4 on the bottom, which means I can bring it out as a 2 on the bottom or a 1/2 in front of my fraction or in front of my integral. And then I need to be able to factor this, if possible, at least that's the goal, into a perfect square, like 2 pieces that are perfect, right? They're exactly the same, I should say. So in order to get x to the 8th factored, it would have to be x to the 4th and x to the 4th. Because my signs are both positive in the trinomial, the signs will both be positive here as well. And then the x to the negative 8 will be factored as x to the negative 4th and x to the negative 4th. Now, if you compare this to the part in yellow, going backwards right here, you see that they're the same except for the signs, right? This is a very friendly one. This isn't going to happen in all of our problems, but I wanted you to see that sometimes it does. And in particular, the directions here don't indicate that we should have to use any graphing device or calculator in order to do it. So the directions lead us to believe there's going to be a way to do this by hand. And there is on this one. I'll show you what happens with the directions when you're not led to believe that in a moment. But this is actually a perfect match. So in some sense, we could rewrite this if necessary. You don't necessarily have to rewrite it this way, but this is the square root of this thing squared, right? Which means that the square root and the square cancel. And I'm left with the integral from 2 to 5 of x to the 4th minus plus x to the negative 4th dx. Yes? Okay, wonderful. These are both easy things to integrate, as long as we integrate, right? And don't do a derivative now. As long as we integrate, they're easy things to integrate. So I have a 1/2 in front. What is the integral of x to the 4th?
X to the 5th over 5.
Wonderful, x to the 5th over 5. How about an integral of x to the negative 4?
X to the negative 3 over negative 3.
There we go, x to the negative 3 over negative 3. And I'm supposed to be evaluating this 5 down to 2. We're going to show the step at least where we plug the 5 and the 2 in, and then you're welcome to use your calculator to simplify it from there if you'd like. So the 1/2 will be at the front. We're going to put the 5 in. So this is 5 to the 5th. Whoa, that doesn't look very good. Let's try that again. 5 to the 5th over 5. And then you might want to rewrite this just for it looking a little bit easier to work with if you were wanting to do it by hand, perhaps. This would be negative at the beginning, and this would be a 1 over 3x cubed. That's what it would be if I rewrite it in sort of a more standard form. So I'll write mine in this way. So I have a minus 1 over 3, and then I have 5 cubed. All of that is subtracting, plugging in the same thing, or plugging in the 2 into the same thing. So 2 to the 5th over 5 minus 1 over 3 times 2 cubed. And then close that bracket. Okay, so grab calculator. Let your calculator do the mess. And simplify. If you ended up with a repeating decimal, we need to make sure we don't write it in repeating decimal form, of course. We want a fractional form. This one doesn't, so you can either write this one in fractional form or decimal form. And the directions don't tell us to round to anything, so we'll write the whole decimal out if we choose to use decimal form. So somebody tell me what you get when you find this either in decimal or fractional form. Make sure and distribute through the 1/2 after you've done the evaluation if you're doing those in steps. Does anyone have a value?
309.3221667.
Okay, I have 309 point something. I don't have that decimal expansion though. 3195 is what I have. So check. You found your data entry error? Okay, no problem. So this is the decimal. And of course, if WebAssign or if the directions in a problem tell you to round to something, of course you're going to round to something. But this is a stopping decimal, so we'll write the whole thing out since we don't have any indication. If you turn this back into a fraction, so on your calculators, if you hit that math frac button and turn it back into a fraction, it's ugly looking, but just so you have it written down, it's 618,639 over 2,000, just so you know. And either of those versions would be fine. Again, if the decimal had stayed at like a repeating decimal or you couldn't see how it was going to terminate, then the fractional form would be our preference. Okay, everybody good with that? Okay, but we need to recognize that this one was really friendly, not in the sense that maybe it was easy, but in the sense that it factored at the end and the square root and the square root canceled, right? That was very, I don't know, special is not really the right word, but it's very unique. It does not happen all the time. So there are going to be some examples where you're not going to be able to cancel a square and a square root and take an integral in a very nice fashion. It's going to happen. And when that happens and you're not expected to actually find the antiderivative, you'll see directions look something like this. What part of this directions tell you that we're going to not be able to do something? Yep, help of a graphing utility. That's a pretty good red flag to say that it's not going to be able to be done without it. Okay? And if it is able to be done without it, then it's giving you permission to use it anyway. But mostly you're going to be using that when it's not able to be done without it. So keep that in mind as we work. Now, setting it all up and everything is still on us. We still have to create all of those pieces on the original setup, or the calculator doesn't help us anyway. So the original problem is asking us, again, for arc length. And we're given a function that's actually a fairly nice one. It's 1 over x. And of course, we can rewrite this as x to the negative 1. So our first step, just like our first step on the last one, is to take the derivative. So what is the derivative of x to the negative 1?
Negative x to the negative 2.
Right. Negative x to the negative 2. If it were the antiderivative, we'd be looking at logs. But this is a derivative, so it's negative x to the negative 1, just like last semester, okay? Very good. So then we're going to do, and you can rewrite it if you wish. as 1 over x squared either way. You're going to do the integral from the limits of integration they give you, which is 1 to 3. This is my arc length of the square root of 1 plus either of those versions. Since I changed mine, there's a negative missing. Negative 1 over x to the x to the 2 squared like this. If you want to leave it written as negative x to the negative 2, that's fine too. It doesn't matter. All right, so we're going to square this piece inside. Yeah? So as we square this piece inside, I have 1 plus 1 over x to the 4th dx. Everybody good? Okay. There are ways to do this by hand. Let me just make that comment real quick. But we haven't learned them. They're in chapter 8. So that's why this directions is talking about taking things with a graphing utility. This one looks quite different than the last one at this point. Can you tell me what about this tells you that this is not going to be as simple as the last one to do, or at least done in the same way? That is, I'm not going to be able to factor it and cancel out a factoring of the square and the, not cancel out a factor, but cancel the square and the square root. Why am I not going to be able to do that on this? Can you tell? Why will I not be able to do this and make something work?
Because x is in the denominator?
We could have written it as x to the negative 4th, and it wouldn't be, though. Right? The other one had an x to the negative 4th or negative 8, and we actually could have had a denominator too. So it's not the denominator part.
Can't factor that out.
Okay, why?
Because you can't break that as something that'll multiply to it because it's not squared. There's only two values.
There you go. All right, this is a binomial, right? 1 plus x to the negative 4th or 1 plus 1 over x to the 4th. This is a binomial. Okay, binomials will only factor like this if they were a difference of squares, and even if it did that, and this is not a difference, it's a sum, and even if they did, it wouldn't be helpful if it were a difference of squares because it wouldn't be the same thing squared and able to cancel the square root, right? So this is a sum. It actually is a sum of squares. A sum of squares does not factor into perfect or the identical pieces squared. They just don't factor that way. So that doesn't help us. And in particular, it doesn't factor at all. Sums of squares don't in the real number system. They do in the complex number system, but they don't in the real number system. So this doesn't work. Right? It does not factor. So because it will not factor for what we're doing at the moment, we're stopped. Now, there are ways to clean this up. Imagine if we would have separated this, right? I could write this as x squared over x squared, the number, the one at the beginning, right? And the numerator would be x squared plus 1. Sorry, not x squared, x to the 4th plus 1 in the numerator. The denominator would be x to the 4th. I could take a square root of the denominator, kind of like I did my 1/2, brought it out. I could bring it out as 1 over x squared. There are some things that we could manipulate and see if we could use some other forms of integration, but we don't have those other methods. The only method we have right now is use substitution. This one won't work with use substitution. So we get stuck again, okay? So at this point, the beautiful thing is that the only thing you can do is go to calculator, right? So grab your calculator out. I want you to put in this whole expression, including the square root, into y1. So you're going to have the square root of 1 plus either 1 over x to the 4th or x to the negative 4th. And you're going to do one of two options. So I'll remind you of these. We've done these this semester already, but F and INT, that's underneath Math 9. So you can choose Math 9. One of the versions of the calculators you guys have you put it in as y1, x, comma, and your limits of integration are 1 and 3. That's an older version. Some of you have ones that will pull up this bracketing right now, and you have to put the 1 and the 3 here. You have to tell it y1 here, and then you have to tell it dx at the end. So these are the 4 locations in the older version. These are the 4 locations you fill in the newer version of the calculator. Either of those choices will then allow you to find the integration. The other place you can do this is in the graph. Remember, we have that place where it shades things in from left to right. It's really nice and sort of visually appealing, you can do it from there as well. We'll do just this one for here. And it doesn't have directions up here that tell us, so let's just say that we're going to round to 3 decimals. We'll have to tell you in your problems, and I didn't put that in there. I didn't think to write that as part of my directions, so we'll go with that. So let's go Math 9 on mine. And I have 2.147. Does that sound right? Yes? Yeah? Okay, great. So this is our antiderivatives value, our definite integral, our arc length. Okay, ready to switch gears for the other thing in this section? All right, notice what we didn't have to do on these. There was no need to draw any pictures. Everything we've done from 7.1 to 7.3, actually last time, so 7.1, 7.2, 7.3, pretty much hinged on us being able to draw the image, correct? Without that, we're sort of left guessing some things along the way, and we may or may not guess correctly kind of stuff, so an image was helpful. There's no need to draw the arc length to be able to utilize the formula. But as we shift to our other one, surfaces of revolution, we are going to be back to the point of having to draw some images, okay? So this is the surface of the solid of revolution. So here are our formulas. So we're going to let f of x have a continuous derivative, and capital S will be the area of the surface. I didn't call it capital S, your book does. I think A would probably be better, but it doesn't. Capital S is the area of the surface of the solid of revolution. So we have 2 versions again. Is it defined in terms of x or defined in terms of y? So one option is that you have 2 pi times the integral from a to b of r of x, and then you see that same piece, square root of 1 plus f prime of x squared, right? That same piece we've been working with, dx. Or you have the integral that's got the 2 pi in front that has from c to d of r of y, and then you have the same component from the distance or the arc length formula of the square root of 1 plus g prime of y squared dy. Okay, so looking at the differences of this compared to like the arc length formula, what do you notice has showed up that wasn't there before?
The R of X.
Okay, the r of x or the r of y, that's one piece, yes. Okay, what else? The 2 pi at the beginning. So 2 pi gives us this 3-dimensional effect, right? We're going around an axis. This is revolving around something. That 2 pi is much like what happened when we were doing the solid of revolution. And the same thing for the r of x or r of y. It's the radius. And it gives you a description. R of x or r of y is the distance between the axis of revolution and the graph of the function. It's always the distance between the axis of revolution and the graph of the function. It's the radius of our spinning object, okay? So we're going to be drawing a representative rectangle to identify that radius as we work our way through. So this is going to most closely mimic, if you will, discs, if you want to sort of jot down a note for yourself. In other words, our representative rectangle is going to be perpendicular. And as we draw it, I think you'll see why that makes sense with the way that this has been set up. Okay, ready to do an example? Okay, so we do need a picture. This is finding the surface or area generated by rotating around the x-axis. So we need to know that it's the x-axis. We have an image, whether you put this in your calculator to draw it, which is fine if you wish, to put in square root of 9 minus x squared, or where you think about what it would be if you sort of squared both sides and so forth. Do you know what this is an image of? Does anybody know? Okay, let's think through what would happen if we squared it. I know your calculator did it for you too. If you squared both sides, what would you get?
9 minus x squared.
9 minus x squared on the left, or on the right, and what would be on the left? Y squared. So it would say y squared equals 9 minus x squared. What if you move the x squared to the other side? Yes. So it would say x squared plus y squared equals 9. That's an equation of a circle. Now, the fact is we don't have the whole circle because it doesn't say plus or minus this, right? This is going to be a semicircle. It's the top half of a circle of radius what? 3. Thank you. Goes from 3 to -3 and 3 at the top. Now, we're not integrating from 3 to -3. We're only integrating from -2 to 2. So our image will look like this. And you don't have to reason through it the way we just sort of verbalized that. Your calculator will draw this for you just fine too. It won't necessarily look very circular because the screen on your calculator is a rectangle as opposed to a square. So it'll kind of look like an ellipse a little bit more, or kind of like an oval kind of shape. But this is our image of what we're trying to integrate. And we're spinning it around which axis? The x-axis. So when we draw our representative rectangle, how will it look? Perpendicular to the x-axis. So it'll look like a tall rectangle like this, right? Everybody good with that? And the radius is going to be the height of this rectangle. Let me draw it on the other side. I have more space to write. So this is my radius. What is this radius? It's y. The height of the rectangle, this is delta x. It's the change in x. So in terms of which integral am I going to use, because I had two formulas, I'm going to use the integral that has the x in it. So this is my s equals 2 pi. This is from a to b of r of x, and then I have the square root of 1 plus f prime of x squared dx. Okay? So once again, the representative rectangle determines, do I do r of x or r of y? Yeah? And I'm working with, I still haven't done the derivative part yet, but I'm working with a semicircle on this one. Okay, so we need a derivative of this before we can go any further. So I need y prime. What will the derivative of the square root of 9 minus x squared be? 1/2. 9 minus x squared to what power? -1/2 times -2x. Okay, it's a chain rule. You've been working with that one for several months now. These 2's will cancel. I can rewrite this with an x on top and the square root of 9 minus x squared on bottom. Negative. Thank you. Okay, are we good? And what will my r of x be? It'll be the height, which is my y value, which is the square root of 9 minus x squared. So these are the two pieces that I need in order to set up my integral. And this looks like it's going to be awful, and you're going to be very pleased and surprised at how quickly it cleans up and simplifies. All right, a and b are going to be what? -2 and 2. R of x is the square root of 9 minus x squared. And then I have 1 plus -x over the square root of 9 minus x squared, all squared. Admittedly, it looks terrible, right? It looks bad. I do see some things that look like they might simplify, right? I've got a square root of 9 minus x squared out here, and there seems to be a square root of 9 minus x squared underneath somehow. So maybe there's a chance that some things are going to collapse, and they are. But it's going to clean up really quickly, okay? So we're going to take it step by step. We're first going to square what's inside the parentheses. So I have 2 pi at the beginning, integral -2 to 2 still, square root of 9 minus x squared, none of that's changing. And then I have 1. Now I have -x on top, so that's going to become just, when I square it, it's going to become just x squared. So I don't actually get any more negatives. And the denominator just becomes 9 minus x squared, correct? Okay. Now I need to combine this 9 minus x squared denominator with this 1 that's at the beginning, right? I need to get a common denominator to do that. Because this is going to get a little bit longer, I'm going to move to the next slide to finish it. Okay, so I have my 2 pi my integral from negative 2 to 2. I have my square root of 9 minus x squared. And then we're going to have this denominator, or this fraction, this value 1, written as a fraction, which would be 9 minus x squared. And then I have the plus x squared that's happening over here, all over 9 minus x squared. So I got a common denominator and combined the fractions in one step. Is that okay?
Yep.
Okay. But notice what happens in the numerator now. What does that become? Just 9. These add to 0. That becomes a 9. And just like we had done on an earlier problem, we can separate out the square root to apply to the numerator and the denominator separately. So I have this as square root of 9, and I can have this as square root of 9 minus x squared, and lo and behold, what do you see happening? Yeah, the 9 minus x squareds underneath the square roots cancel. I also have a square root of 9, and what's the square root of 9? 3. So this is 2 pi times the integral from negative 2 to 2 of 3 dx. Whoa. That's way better. Yeah? Yeah, it is. So what is the antiderivative of 3? 3x evaluated at 2 and negative 2. So we're going to take 2 pi, 3 times 2, and then minus 3 times negative 2. And we are going to get 6 plus 6, 12, for a grand total of 24 pi. It should make sense that each of these pieces, that is plugging in 2 and plugging in negative 2, give me the same value, in this case 6, or you could say it's 12 pi if you're multiplying individually by the 2 pi, because our graph is symmetric, right? From 0 over left to the negative 2, or from 0 over to the right of positive 2, I'm getting the same amount of area on both sides because I have symmetry in my graph. All right, any questions? All right.